In this slide, we are going to cover scalar multiplication of vectors, and scalar is just a fancy word for a constant. All right, and a constant in math is just a number that you know, a value, one singular number. Constants are defined by two numbers, right? They're defined by their distance. Well, they're defined as if you're in component form, it's a distance and a direction is what's important for our vectors. So the product of a vector v and a scalar, and another word for scalar, just constant k, is a vector that's in the same direction that is k times as long. So if you have 2 times v, it's going to be the vector v twice as long. All right. So what I have, and a couple things to note: when k is positive, it's extending it in the same direction. When k is negative, it's a vector in the opposite direction. So what I have down here, all right, is examples. This is the visual representation of scalar multiplication. All right. So what we have here is, if this is vector v right here, I'm moving it around. If that's vector v, what we could do is, by copying this, you would be able to get vector v if we paste it. Now, vector negative v, if we paste here, that's not going to be, you're going to have to rotate it a little bit. You're going to flip it a couple times, and actually if we flip it, it's because it's going to be a vector in the exact opposite direction. So this would be vector v over here, vector v over here. This would be vector negative v. Vector 2v would be 2 of these vectors long, twice as long. All right, so it's really just one arrow in the whole direction. That would be vector v, twice as long as v and in the exact same direction. Again, the position doesn't matter. Negative 3v is going to be this vector right here 3 times. So all we would be doing is pasting it a few times. This vector here, paste a few times. This would be a representation of negative 3v. It's in this opposite direction of v. It's 3 times as long. That would be, so that's scalar multiplication. Now that's the actual pictorial representation. We will go over the actual, right down here, what the actual formula is if you have the scalar multiplication. So if you have a vector, let's say we had a component form vector 2, 2, 6, and we want to multiply it by a scalar, make that scalar 3. Well, the new vector would then be 6, 18, and that would be in component form. That would be the scalar multiplication. Now, I think that's pretty easy because it's very similar to distributive property, and I'm sure we'll see it in a few future slides. All right, so sticking with the same theme for vector addition, what I'm going to try to do is give you kind of a visual representation of what vector addition is, and then we'll show how it works with the numbers and the actual vectors itself. So to add vectors, all right, what a vector is it's a starting point and an ending point. All right, and we call those the initial point and the terminal point. And when you add them, you're just going to go from an initial point to a terminal point, and then you're going to put that terminal point, or when you're going to go initial to terminal, you're going to put the next vector's initial point in that same spot, and you'll then go to the final terminal point. So it's like a 2-step process. You're going to essentially, and I'll show you down here. What I have here is vectors u and v, and I want to calculate u plus v. So the way you would represent this, I can take, remember, it doesn't matter that I'm moving it because position doesn't matter. It just matters that I'm keeping the same direction and length. So let's say I put vector u right here. What I then do is position vector v in the position where my terminal point and my initial point overlap. And the new vector u plus v is this right here. This red line would be vector u plus v. It is in the direction of terminal point, call this point here the initial point ending at our terminal point. And that would be the red line vector u plus v. So that's the way to pictorially represent a vector addition. It's always done by putting the second vector's initial point on the first vector's terminal point. I know that's probably a little difficult to picture. But the actual addition and subtraction and scalar multiplication is pretty intuitive. For example, 2v is just 2 times this, so 2v negative 4 comma 10. That would be the vector in component form. If I'm looking for w minus v, that is my x-coordinate minus my x-coordinate, my y-coordinate minus my y-coordinate. So it's going to be 3 minus negative 2, again, component form, comma 4 minus 5, and that's going to be 5 comma negative 1 for w minus v. And if I wanted to do v plus 2w, well, we can do negative 2 comma 5, plus if I think, well, 2w, I can probably do that part in my head. That's 6, 8. And last but not least, I add them together. So I'm adding my x's, adding my y's, and I get 4 comma 13. And again, in component form. So make sure you're making note to use the correct brackets for component form. That's a little different. We don't want to see the parentheses unless it's not in component form. All right. I want to point this out that talking about our notes, this is going to be, there is a properties page on page 412. There's like 10 of them, and I don't think we need to write them all down. They're, in my opinion, relatively intuitive. We are going to discuss those in class the next time I see you. All right, so here's where we pick up, going back to that term, unit vector, which we saw in the last video. A unit vector has a length equal to 1. All right, so if you take a vector, any vector, no matter how long it is, and you divide the entire piece by its length, you will always get a new vector that has a length of 1. So if you want a unit vector, you must divide the current vector by its length. That's what I am saying here. If you want a unit vector, you must take the current vector and divide it by its length, and another word for length is just magnitude. All right, so down here, to find a unit vector, this is however you want to think about it, this says right here, take the vector, divide it by its magnitude. If you don't like the word division, well, you can take scalar multiplication if you prefer. You could think of 1 over the magnitude times the vector. That would be because magnitude is just one singular distance. 1 over the distance, then it would be a scalar multiplication times v. Whatever you prefer to think about it, think of it as, that's how you will find unit vectors, is you take a vector, divide it by its magnitude. All right, so here's an example. Find the unit vector in the direction of v if v is equal to, here's component form, negative 2, 5. So I already know that this v is traveling in the direction negative 2, 5, so I already know it's traveling left and up. What I'm concerned is I really need its magnitude. I need the magnitude of v, which is a distance formula. And when it's in component form, it's even easier. Negative 2 squared plus 5 squared. The magnitude here would be the square root of 29. And if I want the unit vector here, I just take my current vector, negative 2, 5, right, and I'm going to divide it by the square root of 29. All right, now when I do that, both terms, the negative 2 gets divided by the square root of 29, because again, scalar multiplication goes to both of them, and the 5 gets divided by the square root of 29. And if I want to be fancy, then I could rationalize my denominators. Negative 2 radical 29 over 29, comma 5 radical 29 over 29. That would be component form. If you ever wanted to, you could, this is on the, that coordinate would be on the unit circle. You could verify by doing x squared plus y squared. That should equal a guarantee of 1. I'll let you do that on your own time. If you're interested, you could take the whole first fraction and square it, plus the whole second fraction and square that. Plus the the second fraction squared, and that will total 1, I do guarantee it. Okay, so here we start talking about standard unit vectors. There are two standard unit vectors, and they are labeled I and J. Well, the reason they're called standard unit vectors is because I always stands for 1, 0, essentially a vector that is always a distance of 1 to the right. J stands for a vector 0, 1, which is always a vector 1 up. All right? And what it means is because we have these I and J always standing for left and right, think I comes before J in the alphabet. That's why I is similar to an X coordinate and J is similar to your Y coordinate. What we now have is it's just a second notation, is where we call this component form. We also have our standard unit vector notation. We could call this 3I because that's 3 of these to the right and plus negative 4J, and that's because that's 4 of these vectors, negative 4 of those vectors. All right, so you have two ways to write it. Doesn't matter how, whether you write it like this or whether you write it like that. Both are correct. And again, I and J are just another, it's really almost like another way of writing component form if you want to think of it that way. It's the same notation, looks a little bit different. Let U be a vector with initial point 2, -5 and terminal point -1, 3. Write U as a linear combination of standard unit vectors I and J. So to use I and J, first we need that component form, but we don't have that component form because all they did is give us initial points and terminal points. So going back to the beginning of this slide, to get component form, I do terminal minus initial, -1 minus 2, comma, -5. Oh, I'm sorry, wrote that wrong. 3 minus -5. And the component form vector here would be -3, comma 8. All right, how do you turn that into vectors using I and J? Well, now it's -3I plus 8J. All right, so our last problem of today is just really a combination of everything we've done. Whether you want to use component form or you want to use the standard unit vector notation that's been given to us, you're finding 2u minus 3v. This is the same scalar multiplication with slightly different notation. So when I say 2u, well, that's going to be 2 of all of that. So 2u is going to be -6i plus 18j. All right, when I say, well, we can think of it as -3v is -3 of all of that. So we would be thinking of it as adding -6i and positive 3j, and you can now, even at this time, just think of it like terms. You would have -12i plus 21j, and that would be a final answer. Before I go too far, I think I made a small error here. We're just going to change this. That should have been -6i plus 16j. Made a small calculation error there, but the rest stays the same. What it does do is it does change this j. It should have been 12i plus 19j. Hopefully you caught that before I caught that, but the fact is we caught it. Anyway, the next time I see you, we are going to talk about direction angles. There's just a few slides here, but I do want to clarify a couple things involving direction angles, so I look forward to seeing you next time in class.